Good morning, my dear student. Can you hear me?
Yes, sir.
Okay. I'm trying to share the screen. Let me. Okay, can you see my screen now?
Yes,
Yes, sir.
Yes, sir.
Okay, so welcome to this computer organization and architecture course this semester. And this will be taught by Professor Rajat Shubhra Chakraborty, RSc, and myself, Bhargav Bhattacharya, BVB. And as you see that, unfortunately, we again have another online semester. You are already familiar with 2 online semesters, I guess. The last 2 semesters have been online, and we thought that this semester would be physical, but unfortunately, again, we have to go for another online semester. Sometimes online semesters may be frustrating, as you know, and needless to say that this can never substitute the physical, in-class experience. But anyway, we'll try our best to interact with you more efficiently. And please let us know whenever you have any difficulty. All right. So just to give you a few basic introduction. So as you can see that we have started today, 10th August at 10 a.m. And this will continue at middle of November. And we have already uploaded the course description in the Moodle. You can visit that site and download that document. So we'll be meeting 3 times, Monday, Tuesday, Thursday. So this is 3 plus 1. So maybe Thursday we will take some kind of tutorial whenever needed. And most of the classes will be held in real-time mode and occasionally maybe pre-recorded mode, in case we have some other engagement or some other difficulty. But most of the time it will be held in real-time mode so that we can have direct interaction. And tutorials and doubt clearing session will always be held in real-time mode. Now, apart from the theory course, you know that we will run in parallel the lab course, and everybody has to go through this laboratory course as well. All right. Okay, so for this course, we'll maintain a course page, and so all kinds of announcement, assignment, exams, and everything. The presentations, the PPT, the PowerPoint slides, and everything would be available. You can download from the Moodle page. So please enroll yourself using the key. And in this course, we'll be supported by a very good team of TS. So these 4 TS, Rajay Mukherjee, Akash Deep Saha, Rajat Sadhu Khan, and Srikant, they are all experienced and they have assisted us in previous semesters. So in case of any difficulty, don't hesitate to contact any of them. All right. So you know the prerequisite for this course is just basic logic design, whatever you have studied in the last semester. Combinational and ideas, I mean concepts of combinational and sequential circuits, and knowledge of high-level programming language and algorithms which you already have. So maybe in the next class, Thursday, so we'll take a brief quiz, you know. I'll give you some questions on basic logic design and ask you to solve the questions in class, answer them in class. All right. Okay, so regarding the textbook, so we follow this very famous book, Computer Organization and Design by David Peterson and John Hennessy. Now, interestingly, this book is, you know, I mean, has been there in computer curriculum for more than 20 years. The first edition published more than 20 years ago, and till now, this has been one of the very good and widely accepted textbooks all over the world. And so we will mostly use this 2005 edition, which is called the MIPS version. And occasionally we may refer to the RISC-V version, that is 2018 version RISC-V. And as you can see that the second edition, which was very popular book, you know, it was published more than 20 years ago, is 1998. Now, these two gentlemen, Professor Peterson and John Hennessy, you know, Peterson happens to be a professor in the UC Berkeley, and John Hennessy happens to be the president of the Stanford University. And because of their outstanding contribution in this MIPS architecture, so they have been conferred the 2017 ACM Turing Award. So you must have heard of this ACM Turing Award. This is considered as Nobel Prize in Computer Science. So when they introduced, so they were instrumental in introducing what is called this RISC architecture, RISC. Are you familiar with this term, RISC?
No, sir.
Anybody knows the total full form of RISC?
Reduced instruction set. I don't know what C is, sir.
Reduced instruction set computers. Okay. So this is a paradigm based on which the computers are designed, and long ago, Peterson and Hennessy, they were the first person to introduce this concept of RISC, reduced instruction set computer. And no one knew at the time that this RISC architecture would dominate the computer industries even today. Okay. So after retirement, these two gentlemen joined Google as advisors, and incidentally, they are not only outstanding professors. So, for example, John Hennessy, he co-founded a company called MIPS, and Dave Peterson co-founded a company called Sun Microsystems. I don't know whether you have heard of the workstation, the Sun workstations. Those were very powerful computers which dominated maybe a decade ago. And so those two companies were founded by Peterson and Hennessy. In fact, many other companies like Silicon Graphics and so on. So those machines are based on this RISC architecture. Okay. So that's how it was a pioneering contribution in the area of computer architecture. The concept of MIPS, the MIPS assembly language, as we'll learn later on. And also this RISC architecture, reduced instruction set computers. And in fact, the concept of RISC revolutionized the computer architecture, because of the simplicity in their structure, or the simplicity in the instruction set. The design methodology has become very simple compared to the previous complicated design procedures. All right, so this is the textbook which we are going to follow throughout the course, and some further reading maybe occasionally to other important textbook. One of them is by Sarangi, Computer Organization Architecture, McGraw-Hill, India. William Stallings, Computer Organization Architecture, Prentice Hall. And the very old book, John Hayes, Computer Organization and Architecture. When we were student, we used to follow John Hayes' book, because that time the Hennessy Patterson book was not there. All right. So grading policy, let me briefly state the grading policy. So good news is, so we have online semester, so no mid-sem and sem, but we have evaluation at regular intervals, as we have experienced in the previous 2 online semesters. So we'll give homework for practicing, but those homeworks will not be graded. And there will be online exams and quizzes. And this semester, we have some specific windows which were announced in the IIT calendar. So we'll try to conduct exams and quizzes mostly in those windows, and occasionally we can conduct some other quizzes outside that. Well, so that's all about grading policy and textbook. And so let me start with in a lighter mood. So look at this, the nice painting, So this is a painting from 13th century, So it shows that how it depicts the scenario of a classroom. So you can see that the instructor, the Henry, the Henry of Germany, he is conducting a class here, giving lecture here, standing in the podium. And you can see the students here. So the students sitting in the first bench, they are serious, taking notes and so on. So look at the back bench. These 2 guys are talking to each other. Okay, so this guy here, maybe he's thinking something else. And look at this guy, my God, this guy is sleeping. Okay, so this is a typical scenario as depicted as early in 13th century. You can see here. So this is a scenario of delivering lecture to the university student at Bologna in Italy. Okay, so have you heard of the name of Professor Paul Dirac? The famous physicist? Anybody heard of the name of Paul Dirac?
Yes, sir.
What was he famous for? There was a very important statistics in his name.
Yeah, the Dirac number.
Yeah, Dirac number is there. Then the most famous is, the Fermi-Dirac statistics. See, these electrons follow Fermi-Dirac statistics. Well, so when Dirac attended any seminar, it was found that he was seen always to be, he got asleep all the time, Okay, during the classes, during the seminar, and then at the end of the seminar, he became awake and asked a very pertinent and penetrating question. So what I mean that in the class, so there is a saying that what is a lecture? The art of transmitting information from the notes of a teacher to the notes of student without passing through the minds of each other. Okay. So let not our lecture be this type. Okay. So what I suggest that please interact and ask question whenever you find any difficulty and so on. All right. Okay. So let us move into the agenda. So what are we going to do to start with that? Okay, so there we'll talk about the overview of the course. Now you can see the overview of the course in the document, which is already uploaded in the Moodle that describes the course. What are the topics we are going to cover in the course? And we'll walk through the history of computer design, because every computer science student must know this kind of the information regarding the evolution of computer. And we will talk about the famous Moore's law, and then of course the basic components of a computer. We will introduce the most important concept, underlying computer architecture, which is known as the instruction set architecture, ISA. And this term we'll use throughout the course many times, instruction set architecture or ISA, because the understanding of instruction set architecture is most important when you talk about computer organization and computer architecture. And then we'll talk about computer organization and architecture, which is essentially a bottom-up and top-down view. Now, let me ask you a question here. As you can see that this course is concerned with computer organization and architecture, right? So we often talk about computer organization and computer architecture. So what is the difference between these two concepts or these two terminology? Can you throw any light on this question? What is computer organization and what is computer architecture? What does it mean to a layman? Please say something. Computer organization and
maybe organization deals with the organization of software components, and our architecture maybe deals with the hardware components.
Not exactly software and hardware. I mean, so let us just concentrate on the machine itself, Okay. In broad sense, maybe you are correct because, I mean, a computer is not complete unless you have the hardware components and the software components, application software, operating systems, and so on. So let us forget about this, the software component. Let us focus on the hardware itself, the machine itself. So in that perspective, when I say computer organization and what computer architecture, then what they could be. Right. Now, as the name suggests, organization is the collection of the basic components, how they are interconnected or how they are organized, right? So we are essentially concerned with understanding that what are the basic components, basic hardware components which are needed in order to build the machine. Okay. And how to go further down in order to design those individual components. So that's the domain of computer organization. What about computer architecture? Now, as you have just rightly mentioned that, so there will be other software components, right? So these software components are built over and above the hardware machine. Okay. So given that, now please tell me, what do you mean by computer architecture? What the meaning of computer architecture?
So maybe architecture deals with the interconnection between hardware and software components.
To some extent, you are right. Well, because so once we build a machine, then the machine is supposed to perform what? It is supposed to perform certain instructions, right? For example, add two numbers. Okay, shift the component of a register by 2 bits. This kind of operations, right? As far as the hardware is concerned, isn't so? So given a machine or given a hardware, given some kind of hardware system, that hardware is supposed to perform certain basic operations, right? And based on those basic operations, you will build up the software envelope layer by layer. In other words, so as a software engineer, when you look at the machine, so the machine has certain behavioral aspects, right? The machine has certain behavioral perspective. And based on those behavioral perspective, that means what power the machine, what kind of operations the machine is able to perform. Based on that information, the upper layer of software will be developed layer by layer, isn't so? So we will discuss more about this. So to start with, please understand that computer organization deals with the interconnection and how the internal components are built. Whereas by computer architecture mean is the behavioral perspective of the machine as seen from the machine language programmer and as seen from the other software developers. So basically it's a bottom up and top down view, and we will talk about that more about this concept later on. Okay, that's why we talk about computer organization and computer architecture. These two are different terminology, and the course is also like this, COA, computer organization and architecture. So in this course, what is our goal? What are the goals to understand? Okay, so what are the principles of a computer design? Suppose after graduation, you join Intel company, and you are asked to design the new generation of processors as the technical leader of some group. Okay, so you must understand that what are the consideration or factors you need to consider when you are entrusted with the task of designing a new computer. Isn't so? So we need to understand the basic principles of computer design. What are the cost factors? What is the economics behind it? What is the performance behind it? What kind of performance is expected out of the machine you are going to design, right? So essentially two things. One is cost of the machine you are going to design, and another is the performance you are going to expect out of it. Performance means the speed of the computer, the capability of the computer, the power of the computer, and so on. So these are the principles of computer design. Now, what is the hardware-software interface? Now, this is a fuzzy area, from a theoretical aspect, what do you mean by hardware and software? So you have a problem and you want to have a solution. Now, by hardware mean it's some kind of permanent solution, right? So you design a circuit which takes the encoded information of the input as input, and will produce the encoded output. Whereas by software we mean, okay, this possibly you have a machine for executing the software, and you would write some programs and so on, and to execute the software on some basic hardware. So one thing, so there is an interface between the hardware and software. The hardware is provided by the electrical engineers who have built the machine, and then on the top of the hardware you are going to develop other software components. But one thing you might appreciate at this point, that software is not independent. In order to run software, you always need a machine. Okay, but hardware is independent in theory, because we can always design an electrical machine which will not need any software to execute it. But for the purpose of convenience, what we do that we design hardware to make it a general purpose machine, and then use the power of programming to make it a powerful computer architecture. Do you follow it?
Yes, sir.
Yes, sir.
Okay. So remember this point that hardware is independent. It can independently perform any task, but software cannot. It is always dependent on the hardware machine. So as I also mentioned that this computer organization and versus computer architecture, and we will discuss more about this throughout this course. So one question is that where should I start? Should we think of computer organization first, and then analyze what kind of architecture is supported by it, or the vice versa? Should I specify my computer architecture and then try to build a machine with certain organization that supports computer architecture? So this is a question. This is a dual question. So from where we should start? Whether we should start in order to design a computer in order to arrive at the final product. Where should I start? Should I start from computer organization and end up with computer architecture, or should I specify my computer architecture first and then go down below to design my computer organization? Okay, and this understanding between this dilemma is the whole issue in the study of computer organization and architecture. Another fundamental question here, how to design the instruction set of a machine. So you are familiar with some instruction set or assembly language set of the machine?
No.
No,
Not
sir.
yet, right? No, but have you heard of some basic operations of assembly language?
Yes, sir.
For example?
Move and add.
Move, load.
Yeah, move and add and so on. See, high-level language, you are already experienced. You have written program in C, C++, Python, and so on, Okay. But the bottom line is that finally everything has to be compiled to machine-readable code or the binary code, and that has to be executed on the hardware, which understands only zeros and one, right? So everything has to be translated. When you write a program in high-level language, that has to be translated. That means that has to be compiled into a sequence of machine level instruction, like as you said, that move, add, and so on. All right. So here is a fundamental question. When you are going to design a processor or a computer, how do I design the instruction set of a machine? How many instructions should be there in the machine? What should be the format of those instruction set? Okay. You have to make sure whether the set of instruction is complete and orthogonal. That means there should not be any redundancy, but at the same time, the set of instruction, the basic instructions or machine level instruction must be complete in the sense that given any high level construct, you would be able to compile it down to the instruction set available to the machine, right? So designing instruction set, or the machine level instruction set of hardware is very fundamental when you talk about this computer organization and architecture, right? So for example, you said move, add, what else? Okay. So in this course, we will try to understand, how to design this instruction set of the machine, and the instruction set which you are going to consider for this course is called MIPS. And that was also introduced by the founders of RISC Machine. And in the computer lab course, you will write programs using MIPS language and so on. So you will learn more about it later on. Okay. So another fundamental question is the following. So you have the instruction set like move, add, and so on, and other instructions. Now, so those are assembly level instructions in the sense that they are mnemonics. You write move R1 to R2. That means move the content of register R1 to register R2 and so on. But this word move is not understood by the hardware, right? Because hardware understands only sequence of zeros and one. It's an electrical machine. Okay, so we encounter another fundamental question. Given an instruction set of the machine, like the assembly language instruction set of the machine, how you focus on one instruction set, consider one instruction set, how that instruction set will be executed in the machine. How the hardware beneath it, would understand the instruction set and execute it to perform the desired operation. How the different hardware components should be synchronized with each other so that the desired performance, the desired instruction, the desired operation is accomplished. So do you see the difficulty in implementing this kind of constructs? Okay.
Yes, sir.
Okay. And then another fundamental question, because everybody wants speed, right? We are talking about, see, during our time, machines were very slow, So now we are talking about 2 gigahertz, 4 gigahertz, and so on, Okay. So everybody is trying to have very fast machine. So the basic question is, what are the techniques for performing fast computation? So should the responsibility lie on hardware or should the responsibility lie on software? In order to achieve this, in order to achieve speed, Or in other words, performance of the machine?
Both.
Huh?
Both.
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 Good. Yes. So essentially, you have, of course, by writing good programs, by writing good, by writing efficient compilers, you can speed up the performance of your software interface. And you need faster machine also, right? The faster hardware also in order to execute those instructions. So what are the limitations? What are the considerations so that the hardware can be made faster? There are some fundamental limitations, beyond which you cannot do it. And then this $100 billion question, how to design a complete processor. So in the next slides, in the next few slides, I will show the complexity of the modern machines. And then you will realize that what a gigantic task it is, in order to build a complete processor, which you encounter nowadays. Okay. So in this course, we are going to cover or going to address these questions and see how these questions can be answered. So let me start with a very silly question, what is a computer? So you guys now are immersed in technology, and to a student today, this is a very silly question. Computers have become inevitable in every sphere of society nowadays, and they are considered as, somewhat similar to fire and electricity, right? So you see it everywhere, in your laptops, in your tablets, in robotics, in automobile, in space, in aerospace. So then in Internet of Things everywhere. So there is no escape from using computers nowadays. So in banking everywhere. So, but so for example, let us look into this BMW 345i car. So there is a question whether this is a car or computer. So if you look down into the dashboard, you will see many interesting facts here. So this car, when it is run, if we drive this car, so in the background, so you are running so many lines of code, and there are 53 8-bit microprocessors. Well, microprocessors are basically CPU, central processing unit, and each microprocessor is nothing but a microcomputer. So there are 53 microcomputers inside. There are 11 32-bit microprocessors. There are 7 16-bit microprocessors. So this is just an example that the all-pervasiveness of computer nowadays, which is penetrating in every aspect of our society. So we are going through computer revolution, just like industrial revolution a couple centuries ago. So now you have computers in automobiles. Your cell phone is nothing but a small computer. In the Human Genome Project, World Wide Web, another technological marvel. The search engine, they are all pervasive. You have personal computers, you have servers, you have cloud, you have Internet of Things, and so on. So they are everywhere nowadays. Some computers are called supercomputers. So they are special purpose. So they are designed in order to solve very high-end scientific and engineering calculations. So for example, computations involving space travel, computation involving, say, nuclear reaction or cosmology. They need huge amount of data and huge amount of computation. So they represent the highest capability, but of course they have a small fraction of the overall computer market. The broad market, obviously, the market of the laptops, PCs, the servers, the Internet of Things, the autonomous vehicles, robotics, and almost in all areas of engineering and so on. So, in summary, in short, can you say that a computer is nothing but a general purpose machine which can process information and yield result? Agreed?
Yes, sir.
Okay. However, centuries ago, by a computer, we are going through, let us go through the history of computer evolution a little bit, so that you can appreciate the gradual build up of the gradual growth of the complexities. Centuries ago, by a computer is meant this kind of device. So essentially by computation, we mean arithmetic computation, right? Addition, subtraction, multiplication, and division. Those are the basic components of computation. So what is it?
The abacus.
Yes. So this is the 19th century computer, Or Chinese abacus. Numbers are entered by sliding the bits, and you do certain operations. It can perform addition, subtraction, etc. There are certain algorithms of procedure for encoding the input and reading out the output. Okay, so that was the first computing machine. Have you heard of the name of this guy, John Napier?
Yes, sir.
What was he famous for?
The natural logarithm.
Very natural logarithm, right? So when we were student in school, we used to have log tables for computation, And this is based on the very fundamental operation. You know that, see, the multiplication is difficult, right? If we are given two big numbers with fractions or decimal numbers, so A times B. So the multiplication of two big numbers is difficult, right? So using logarithm, you can do it simply, in a simpler way. How? Because if you take the log of A times B, this is nothing but log A plus log B, right? In other words, when you do this logarithmic transformation, the complexity of multiplication reduces to that of addition, which is much simpler, right? Because addition is a much simpler operation. So therefore, if you have a mechanism of computing the logarithm of a number, you can simply sum them up and take the antilog of that, so it's to restore the original product. And similarly, as you can see, the division is complicated than subtraction. But in the logarithmic domain, a division is transformed into a subtraction process. So in order to facilitate computation, people used to have this logarithm table, or log tables, where given two numbers A and B, you look at the table and you find the value of log A and log B. So you copy those two numbers, then perform addition, and look at the antilog table and compute the antilog of the sum, you get the product of A and B. And similarly division. Okay. So as you can see, this is some sort of first step in computing which facilitates or which expedites the computation process. And later on, so this tabular version, where what you are looking manually in the table and so on, later on there was a device, there was a very famous device which were widely used by engineers decades ago, which is based on the principle of this logarithm. You know what?
Napier's bone.
Well, this is called slide rule. Have you heard of this term, slide rule? So when we were students in the university, we used to use this slide rule. So essentially, this is a scale, as you can see. On the scale, there are some numbers are engraved on it, and there is a slide. You can slide this, and inside there is also another rule which you can slide inside out, So typically there are some movements, these horizontal movements of, so this internal slide and this external slide, So given two numbers, essentially you find the log of those two numbers and compute the addition operation using this slide operation. So this is a very widely used and very simple instrument which are widely used by engineers. In fact, when we were student in our electrical machines lab, we use this kind of device, to compute, multiplication and division very fast. What you need is a sequence of slide operation, and so that you encode the input and then finally read out the output, which is the result of a sequence of multiplication and division that can be performed very efficiently. Interesting. Okay. Well, so let us move ahead. So this is an engine. If we look carefully, there's some digits are engraved on the wheels, like 0, 1, 2, 3, 4, and so on. I'm sure some of you must have seen this picture earlier somewhere. Okay, this is a mechanical machine, right?
The analytical engine.
Sort of, this is Babel's difference engine. Yes, analytical engine was built later, I guess. This is the first mechanical computer, 1832, 300 years ago. Well, you might ask, well, sir, this was the device. This was the technology 300 years ago. What would I do by learning this? But it is important to know the evolution of technology. You will see that how engineers felt difficulties at different point of time and how they overcome it. Okay, so this is the computer which people used in 300 years ago. Now, this is a picture from 2021, which has hit the newspaper last month. Has anybody noticed this picture?
Is it a data mining center? Like
sort of, yeah, but this is a quantum computer reported last month, July 2021 from China. It's called Zhuangzi. Okay, so you have the technology 300 years ago on the left side. You have the technology now in 2021. This Zhuangzi quantum computer built by China. And China claims that this computer has beaten Google, and they claim that it is now world's most powerful quantum computer. So they claim that it solves a problem in around an hour, which would take the world's most powerful supercomputer to solve in 8 years. Okay, please read this article, which will be available, which is reported here. So now you can see this entire spectrum of technology starting from 300 years, the first step in computing, and the most latest, the technology of quantum computing, July 2021. Okay. So in order to understand the growth of technology through this broad spectrum, so that is the purpose of this kind of course. How computer organization and architecture has finally led to this kind of quantum computation nowadays. However, for our course, we will not talk about quantum computing. We'll focus on classical computing only, because it is important to first understand the fundamentals. If anybody of you is interested, you can take further advanced courses in quantum computing later on. Okay, but just to make you aware of the entire spectrum of technology, I am showing you this kind of slides. All right. Let us go through the history a little bit to appreciate the journey of this, the history of computing. So this is Professor Carnot Juice, and he built a machine called Z3. This is the first programmable computer in Germany. So that means you can write a program. It's a sort of general purpose computer, in the sense that you can write a program and the computer can execute the program for different users. Okay, so that's in 1941. So just before, during the Second World War, as you can see. Okay, so let us move ahead, and this is a very famous picture. I'm sure some of you have already seen it. This is the world's first electronic computer. So previously in the computer there are mechanical parts, moving gears and so on. So this is first electronic computer. That means fully solid state. That means no moving part. Okay, but it was built with vacuum tubes and so on, because at that time transistors were not there. So what is the full form of ENIAC? Just for historical interest?
Electronic numeric integrator and computer.
Right. Electronic numerical integrator and computer. See, this is the time, as you can see, 1943-46, time of Second World War, right? So they wanted to, in military, they wanted to compute the trajectory of the missiles and, and so on. And in order to do that, they had to solve many differential equations. And they had to solve many integrations, which were performed by doing numerical integration techniques. And that's why the name of the machine is like this, like electronic numerical integrator and computer. Well, some interesting data here. See, this is the first electronic computer, and see that you can see that. So there are that use 18,000 vacuum tubes, 30 ton. The floor area, the area needed to house this kind of computer is just like a big apartment you needed, So now you can appreciate, so we started with electronic computers with this big. So now you have an electronic computer in your pocket, like in your mobile phone. Okay. So what kind of device density you have achieved? The technologists have achieved in so many decades, right? And so this is two professors, John Muchley and a graduate student, Eckert. So they built this computer at the University of Pennsylvania in Philadelphia, Moore School of Electrical Engineering. So if you visit University of Pennsylvania at Philadelphia, you would be able to see the museum up where some components of the ENIAC machine is still preserved in. Okay. So this is an interesting advertisement, So this is an advertisement, as you can see, for US Army. So it says that how much is cube root of 2589 to the power 16? So what they're saying that please join Army, that because Army has acquired this ENIAC. And if you join here, you would be able to compute, you would be able to get experience in computing this kind of complicated arithmetic. Okay. So this advertisement shows the amazing computing power of ENIAC. In the picture on the right, so there some fault has occurred, and the technician tracks down how to fix it. So this is the time, this is around 1946. Okay. Just after Second World War. So to highlight, so these are the, like in what you call the first generation of computers in late 1940s and 50s. So the stored program concept has already arrived. That means you can write a program and store it in memory of the computer, and the computer would execute those instructions from memory in sort of general purpose idea machine. And those computers are programmed in assembly language because at that time no high-level language was known, no compilers was there. Okay, so you have to write programs using add, move, shift, this kind of language. Like you did if you write programs for microprocessors, you can still write in assembly language and so on. Or in your laboratory, experiments, you will write programs in assembly language MIPS, similar to, and so in similar language, you have to write programs like that. Now, as far as the memory is concerned, people used magnetic devices because semiconductor memory that time was not available, And typical examples of first generation computers are IAS. This is Institute of Advanced Studies in Princeton. ENIAC we have already seen. EDVAC. Okay. this is what is called that electronic discrete variable and computer arithmetic, UNIVAC, universal computer, Mark 1, IBM 701, and so on. Okay, so these are called first generation of computers. Second generation, as you move on, 1955 to 64. So now the transistor technology has arrived, and they have replaced all this bulky vacuum tubes. Okay, so now we have magnetic core memories. The concept of one important thing is here, this concept of floating point arithmetic. So that has been introduced. So this concept of floating point arithmetic allows you to perform arithmetic in using fractional numbers. Previously, machines can handle only integers. Some high-level language arrived at that time. Those are called ALGOL, algorithmic language, COBOL, common business-oriented language, and FORTRAN, formula translation. So those languages are not used nowadays, but COBOL has been very popular, and it has been used even a decade ago, in many business organizations. FORTRAN is even used, in some scientific. I mean, many physicists used FORTRAN nowadays, till now. And also at the same time, the concept of compiler, subroutine library, batch processing, I mean, operating system, those kind of advancement were experienced during that time. An example of this second generation machine is IBM 7094. Okay. So moving ahead, so the third generation is very important. So this is beyond 1965. And here we experience what is called the integrated circuit or IC technology. So that means the entire circuit is fabricated on a semiconductor chip. So there are no loose wires. So that means everything has become compact. The area has become very small. The size becomes very small to build a processor. And semiconductor memories have arrived. So therefore the sizes of memory, the capacity has increased, the cost has reduced, and also the technology has become, it becomes very compact. And in the area of OS, in the operating system, the concepts of memory hierarchy, like the cache memory and virtual memory, those kind of concepts have been developed and implemented. And so therefore the memory transactions could become faster. In other words, the speed of the machine increased, keep on increasing because of this uses of these technologies. The concepts of parallel processing, pipelining also came, time sharing, microprogramming, and so on came. Typical examples of IBM 360, 370 ELIAC. ELIAC is, this is developed in the University of Illinois. Okay, this is called Illinois Automatic Computer, and they built the computer for for NASA mainly. Later on, this DEC and PDP and VAX and AMDAL 470. Those are the machines belonging to third generation computer. They use technologies, semiconductor technology, memory hierarchy, pipelining, and so on. So we will study about this, memory hierarchy, pipelining, so in our course later on. So gradually, as you can see, more and more technologies are becoming available, and computers and people could build more and more powerful computers. So once again, just walking through the history, just look at this interesting picture here. What is it?
Capacitor.
Sorry?
Capacitor.
Well, these are batteries, So this, you see, there are two poles. So there are two batteries are connected in series. So essentially, this is a power supply, Okay. So here there is a small machine is here, right? You can see it. And see here there are two switches. These switches, if I press this switch, the switch will be on. If I release it by spring action, the switch will be off. So there are two switches, So if I push down one switch, it means that this switch becomes on. It becomes 1, logic 1. If I release it, it becomes 0. So So you can insert, you can input 2 bits here, using these 2 switches, you can input you can input 2-bit information, either 00 or 01, 10 or 11, right? All right. And you can see there are the two small lamps here. Okay. So this is nothing but a 1-bit binary adder, So you are inputting 2 bits, and these 2 bits may be 00, 01, 10 or 11. Okay. Suppose these 2 bits are 1, 1. So what would be the output? If I add 2 bits, 1 and 1.
10.
Okay. So that's why you see these are the two lamps here, 2 bulbs. So if the bulb glows, it means it's 1. If it doesn't glow, it becomes 0. All right. So you give inputs of 2 bits, and you observe the output here, the result of addition. In other words, this is nothing but a 1-bit binary adder. So this is the technology, several decades ago. This is just 1-bit adder. Okay. So this is the miracle of electronic evolution, So people started with this technology, just 1-bit adder. And this was some kind of memory, So you can see this annular rings. So these are magnetic, these are metallic, these are ferrite rings, And through the ferrite rings, there are, and the 2 rods are passing, one horizontal and vertical. And each ferrite, each ferrite core can be magnetized in clockwise direction or in anti-clockwise direction. So one signifies 0, one signifies another direction signifies 1. So that means each core, each ferrite core, can store either a bit 0 or bit 1. So this is nothing but a memory network. This is nothing but a memory, And that sort of memory was available, like, just 1K bit, just 1024 bit of memory. We are not talking about bytes, just bits of memory. So that was the technology, when people started building computers. So this is the adder, and this is the adder, and this is some kind of memory technology. Well. Okay. So here again, so this is again a historical picture. Can you see something? This is a circular sort of block, and you can see certain layers, right, or certain tracks using white and blue. So what this could be? And you can see that if we look into the periphery, what do you see?
6 volts.
Yeah, there are some terminals here. These are input-output lines. See, these are metal pads. These are input-output lines. And here, interestingly, there is a circuit. But in the circuit, there is no loose wire. Everything is done by metal layers and so on. And there are some junctions. There are different layers of materials here. So why it is interesting? This is the beginning of the first integrated circuit. What you call the integrated circuit, that means the circuit is what? It comprises resistance, capacitances, electron and connections, transistors and so on. So this is a logic circuit. This is a logic circuit which comprises 2 flip-flops. And these blue structures, you can see those are transistors. And using transistors, some flip-flops have been, there are 2 flip-flops have been built here. 1 flip-flop here, another flip-flop here. And these are aluminum connectors. These are wiring and metal connectors. So this is the first integrated circuit which is built by Fairchild in 1961. So this is a very important step in the history of computer design, because the entire circuit is integrated. There is no loose component. Everything is in solid state. So what is the purpose? Because things have become very simple, you know. I mean, if we have this deposition or this diffusion technology, that how to build this circuit, you know. So then once we build the circuit, then it becomes very compact and very convenient to use. And moreover, using the same pattern of these transistors and I mean this kind of patterns, you know, you can duplicate. You can build so many copies of the same IC in an efficient way. The process becomes very simple. So that you can manufacture these chips in bulk, and therefore the cost will reduce. Okay. So this is a very important step in the history of computer organization and architecture, and also in the history of the integrated circuit. Okay, so that is our first step. Okay, as I mentioned, this is the first integrated circuit ever built in 1961. So then, a couple of years ago, you know, Richard Feynman, the famous physicist, the Nobel laureate, so he asked the following question, you know, that why can't you write the entire 24 volumes of Encyclopedia Britannica? So during that time, we didn't have Wikipedia. We had Encyclopedia Britannica, and it's 24 volumes. You know, it is supposed to have almost every information available during that time. Okay. So his question was, can't you compress this entire 24 volumes of Encyclopedia Britannica on the heads of a pin on a small area? Okay. I mean, is it possible to integrate the complexity of so much information, you know, or compress so much information on a small device? And if we look into the technology which is available today, I mean, which we call nanotechnology, and we talk about this kind of thing, right? So that was a dream in 1959, decades ago, but the dream has become reality nowadays. And the first step was, you know, to just build this integrated circuit in 1961. So in some subsequent slides, I will show you that how this computer revolution has progressed and how this integration has developed from has become more and more compact, so that you can build so that you can encapsulate more and more transistors on a small piece of silicon. All right. So these three guys are Intel founders: Andy Grove, Robert Noyce, and Gordon Moore, 1978. And so they are looking into a microchip design here, some Intel microprocessor. And in the history of computers, evolution of computers, you know, the Intel plays a fundamental role, because it was Intel who first announced the world's first microprocessor. So that means the entire processor or CPU is built on a single microchip, fully solid state. So this is the advertisement: a microprogrammable computer on a chip. So you know, when did Intel announce this? The first microprocessor in the 70s. So in November 1971, more than 50 years ago now, right? Or 50 years ago, yes. So Intel first announced this 4004 microprocessor. Okay, so this is a full-fledged computer on a chip, right? So you might wonder that in this microprocessor, how many transistors were there? Just a few thousand. Okay. But this is the first step. when you're entering into the world of microprocessors or CPU. Okay, so in a lighter mood, there is an interesting hypothetical conversation, So Albert Einstein, is teaching physics, and he said some question papers in the final exam. Some student asked, Dr. Einstein, are not the same question as last year? Okay, are not the same question as last year's final exam? You know what Einstein replied? Yes, but this year the answers are different. Now, the message I want to pass on to you is the following. See, this electronic technology changes very fast. So any technology which you embrace today, will quickly pass into obsolescence tomorrow. And this is very apparent in the electronics technology. If you look into this IC technology in the computer development technology, you will see this this evolution in a very significant way. Okay. So in this slide, I'll just summarize this evolution of microprocessors or the evolution of CPUs, and you will see this. You will be amazed to see the progress of technology, the growth of technology in time. So we started with, as I mentioned, the 1970s when Intel announced 4004 microprocessor. So if you look into this diagram, the chip looked like this. So these are the legs, so these are the input-output terminals. And this, as you can see here that the label is visible here, C4004. Okay, and so this is a fully integrated circuit, and the circuit comprises, so this is the number of transistors in T. So it has 2300 transistors here. Okay, so imagine that you are sitting in an auditorium and there are around 2000 seats here. So this chip can be compared, the population of the chip, I mean the number of transistor on the chip can be compared with an auditorium. Okay. As the technology grows, so 10 years later, in 1982, Intel announced this 80286 microprocessor. Okay. So in this microprocessor, see the number of transistors is 134,000. So you see the growth. You see the compaction density, from 2000 to 134,000 in just 10 years of technological progress. And see, this can be compared with a stadium, right? Moving ahead, in 1999, when Pentium 3 announced by Intel, so this chip, this small chip, encapsulates 32 million transistors. And this is the population of Tokyo. So as you can see, this number of transistors is increasing. This is at an amazing rate. Okay, in 2008, Intel announced Core i7. Number of transistors here on this small chip, you know what? 1.3 billion. Can you imagine? This is population of India. So what does it signify? So this is the kind of chip which you will find inside your mobile phone or laptop or whatever, even though we are talking about, this is 2008 technology, more than 10 years ago. So just imagine that. So this is a processor chip. If I have to design a processor with 1.3 billion transistors, so how to accomplish that design? Isn't it a great technological challenge? As an engineer, how to manage interconnecting 1.3 billion transistors on a single piece of, on a tiny piece of silicon, and that too guaranteeing and you have to guarantee its correct functionality with no error, no design error, no interconnection error, and so on. Isn't it amazing? Okay, so engineers have accomplished this, So they have very systematic design methodology. So we will study some of these technologies in this course. So some modern processors, like if we look into the 2004 Intel 15-core Xeon IV, so this tiny chip, this is the die area. Die means, if I look into this semiconductor or the silicon chip, just without the encapsulation or without the packing box and so on, without the packing material and so on. So that is called the basic die. Okay, so the die size, as you can see, this is 6,000 millimeters square, very small. And this encapsulates 4.3 billion transistors. This small chip. This area is this. And this is what is called the 22 nanometer technology. So in IC, we often talk about this nanometer technology. See, 22 nanometer. Now see, 1 nanometer is 10 to the power minus 9, right? So when you talk about this nanometer technology, it means that this is called the feature size of transistors. So as the technology progresses, the transistors, it is possible to fabricate more and more smaller transistors. Okay, so when you say 22 nanometer, it means it signifies the feature size of transistor. That means what should be the separation between two transistors and so on. So those design rules or design specification is given by this technology value. So as the technology progresses, this nanometer value will reduce. The nanometer value reduces. Do you understand it? Okay. Any question here? Are you with me?
Yes, sir.
So this nanometer technology tells you that, I mean, the minuteness of the transistors. I mean, if the transistors become smaller, we will say that this nanometer technology will reduce. Okay. So as you can see that computers are becoming very powerful, and this is an example, that IBM Deep in 1997, IBM Deep Blue machine. See, the Grandmaster Garry Kasparov is playing with a computer, with an IBM computer, and he was defeated. The computer just defeated the Grandmaster. So you see this tremendous growth of artificial intelligence and so on. So this is a later technology, 2016. It encapsulates 7.2 billion transistors on Intel Broadwell Xeon SoC. SoC is system on chip. And as you can see, this is 14 nanometer technology. See, this is technology value reduces. And the latest one is, this 2021 AMD chip. It's called Ryzen processor. So this is 4 billion transistors. And this is 7 nanometer technology. Okay. So what I mean that just if we look into this first, so that was the first integrated circuit, as you can see here in 1961, and coming back in 2021, you have 4 billion transistors. So that's the growth of technology that has been experienced in just few decades. Okay, so moving ahead, so there is a parameter which is called the transistor density, or that is the number of transistors per unit area of the chip. So if you look into this diagram, so this talks about the transistor density in AMD processors. So on the horizontal scale, you see the year, and on the vertical scale, you see the number of transistors. transistor density. That means number of transistor per unit area of the chip. So if we look into this, the present time, 2018, and this is the projected, 2020 and so on. So you can see that this is the transistor density per unit area. It's a huge number, isn't it? Okay. So this transistor density is increasing at an exponential rate, as you can see. And this is the, just for your information, that in 2023, Intel 7 nanometer, this PC chip will arrive using Taiwan TSMC's technology. And they are going to market two products. One is Meteor Lake for PC and Granite Rapids for data centers. And they're using 7 nanometer technology. So that gives you some idea that the feature size of transistors. All right. Technology that one tile over another, the stacking technology that includes the CPU, the central processing units, the graphic unit, and also the AI processors and so on. And approximately 200 million transistor per square millimeter of the chip. So as you can see, this transistor density on chip is growing at an exponential rate. And as the technology progresses, as the technology advances, the transistor density also increases at an exponential rate. And this is captured in what is called Moore's law. So Gordon Moore, one of the co-founders of Intel Corporation, so he in 1965, he stated what is called Moore's law. And this is a law which drives the semiconductor industry now, even now. So this is an empirical law. What he says that he predicted that the number of transistors integrated on a die or integrated on a chip would grow exponentially. That means would double every 12 to 18 months. And that reflects this acceleration of technology. Are you with me?
Yes, sir.
Okay. So this is the driving force of the semiconductor industry. This is he predicted. This is an empirical law that the number of transistors, that means the technology what you see today, after 1 or 2 years, the number of transistors that could be accommodated on the chip might be doubled. And you are looking for more and more powerful machines this way. Okay, that's why the technology is changing so fast, particularly in the semiconductor domain, in computer industry. And that's why you see, you buy one personal computer, one PC, one mobile, it becomes obsolete within a year or so. So new chips would arrive and so on. So this is not only is a matter of technological progress, but also there are a lot of economics behind it, or business, the business factors behind it. In 1980s, this million transistor per chip barrier was crossed. Today, as you can see, that around several billion transistors per chip can now be fabricated, as apparent from the previous slides, right? And so if we look into it, so this is the famous plot which describes the Moore's law. So on the vertical scale, the million transistors, the number of transistors or transistor density, and as you can see, this on the vertical scale, they are in the logarithmic. This is in logarithmic scale. They are getting doubled in every step. I mean, they are getting multiplied. So they are getting multiplied by a factor of 10 on the vertical scale, and this is the linear scale. So in the logarithmic scale, they appear linear. The growth shows linear. It means that the growth is exponential, right? So this shows the transistor count in a chip, and this is what is called this. There is an agency called the International Technological Roadmap of Semiconductors. So they tell you that what kind of technological technological thing are ahead of you. But what you should target for in designing future processors. So this plot reflects nothing but the Moore's law. So remember Moore's law, it talks about the progress of the semiconductor in terms of the number of transistors which can be integrated on a chip. And the empirical law says that the count doubles every 18 or 24 months. So in summary, so this is the photomicrograph of the modern processor. You will see that you can see that this is a multi-core processor. There are 8 cores here and other components here. So this is the whole thing you have to design. So in computer organization, we are talking about this kind of complexities. Today's processor, as you can see, encapsulate billions of transistors or components. So how do I manage to designing such a complex machine? Not only that, in such a complex machine, obviously many design bugs or manufacturing defects would creep in. Okay, your design may be wrong. There may be manufacturing defects. There may be field malfunctioning, right? The transistor, because of aging, they may malfunction. So notice that there are billions of transistors. Even if the single transistor becomes dysfunctional, even if the single transistor becomes dysfunctional, the whole chip might be in jeopardy, isn't so? Because in integrated circuit, you cannot repair a transistor. You have to throw the chip anyway. Because transistors, once integrated, they are not accessible. Everything is integrated on a single piece, on a tiny piece of silicon. So guaranteeing the correctness or defect-free feature of every transistor is very important, so that your performance is reliable and your device is reliable. Okay. So this bug management is another important issue here, particularly in such a large design. So here is an example that why reliability of hardware design or chips are important. Chips are everywhere. In aerocrafts also there are chips, and that's this is a news cutting. The U.S. Airways jet crash, landed in the Hudson River. There was a failure in the computing chip. So you must be careful about how the chips are designed, and so that their operation should be fault free and there should be fault tolerant, so that this kind of accidents could be minimized. Now here is an important piece from history. So this is called the famous Intel Pentium bug. Has anybody heard of this kind of stories?
It causes the floating point operations to get messed up, but so, very rarely so.
Yes. This is a famous story. Intel marketed this chip, Intel Pentium. It is 66 megahertz Intel Pentium. Now, after the chip has been marketed and several laptops and PCs have been built using this kind of chip, later on some bug was discovered. So there was some kind of design bug which involves the floating point division. Okay, so Intel has to, recall all the buggy chips, so which costs, of course, loss of several $1 million to Intel, and not only that, it also provides an important lessons to computer designer. Okay, so the story goes the following. So it's called the floating point division unit. So there is a floating point division unit in the chip, which was realized in hardware. And once the chip was marketed, and it is being used in very different laptops and PCs and so on. So while the machines were, and people were using those laptops and machines, and some chips were discovered by this guy, Professor Nicely at this college in the United States, and then it has been found that 4 to 5 million Pentium chips already produced with this kind of design box. And as a result of that, a lot of errors, and scientists posted many errors and in the internet during September in this time period in 1994, and in November 22, 1994, Intel made some kind of press release. So Intel announced in the press. So then, yes, the chip is buggy and there are some defects here, and this can make errors in the 9th digit of the floating point number. So this error is very small, but still then it's an error. So where very accurate computations are needed, this chip will give erroneous value. The machine would give erroneous computation. So Intel has to recall all these chips. So this is the famous statement given by Intel. It's called Pentium conclusion. And Intel, the loss of Intel was $500 million. So Intel announced the following: to owners of Pentium processor-based computers and the PC community, we at Intel wish to sincerely apologize for our handling of the recently publicized Pentium processor flaw. Intel will exchange the current version of the Pentium for an updated version in which the floating point flaw is corrected for anybody who requested it, free of charge, anytime during the lifetime of the computer. Okay, sincerely. So this is a very interesting story, and it also gives an important lesson that how to design your machines, so that you have to be very careful about the possibility of the existence of design bugs or in subsequently any manufacturing bugs and so on. Okay. So I'll just focus on, just touch upon what kind of computers are in the offing. Some kind of computers may be seen in the future. One of them, as you can see, is the quantum computers we talked about. Well, so in summary, we have trillions of personal computers, laptops and palm tops. We have this networking, wireless, this Internet of Things, system on chips, and this MEMS technology. In future generations, we might be talking about this biological computing, neuromorphic computing, molecular computing, computers based on nanotechnology like carbon nanotube CNT-based CPU, which has been developed in Stanford and many other places recently, and then optical computing. So we normally talk about the computers are built with logic circuits, right? Like AND or gate semiconductors and so on. So here we are talking about different kinds of technology at the basic element, optical computing. So here the computation can be done by light rays only. There are optical AND gates, optical OR gates, and so on. So instead of electronic signals, you have light signals, and you perform logical operation between them. Okay, so in future generation of computing, you might experience this kind of thing. Some of them have already arrived in the market, or already arrived in the industry and so on. But there are a lot of opportunities and new technologies are awaiting ahead of you. Okay. The neuromorphic chips is basically a machine which is built on some kind of artificial intelligence. So it attempts to bridge the gap between the artificial and natural computation. See, the computation performed by human being is different, It's called something neural computing. So the neuromorphic chips are chips which are based on this kind of philosophy. So these chips are based on some kind of deep learning methods, some kind of deep neural network and so on. They deploy deep neural network and other technologies which emulate the neurosciences, the neuroscience, or the basic computing paradigm, which is followed by in the human brain. Although this is not fully understood, but some of the technology has already been in small scale has been built, like what is called this driverless car and so on. So they use this kind of neuromorphic chips. So they will be able to play chess, drive cars, and empower smartphone or personal assistants and so on. Mostly these are built on different kinds of learning technologies which are evolving nowadays. All right. And so this is an example of, like IBM TrueNorth, which is a collection of around 4K processors, 4096 processors, which mimic 1 million human neurons to 56 million synapses, so that they can mimic human brain. Okay, so IBM has taken this kind of project in 2014, and some chips might appear based on this deep neural network and so on. So these technologies might hit you in the market in the near future someday. So they have some kind of artificial intelligence capability, like recognizing people, recognizing objects, so that the machine can maneuver different kinds of obstacles on road and so on. And they have also different kinds of paradigm. They may not separate processor or memory. There are memory set technologies coming up nowadays, which can be used to implement both memory and logic. So those technologies may be available in the future, might hit in the market later on. And Google IBM also announced these IBM computers, the quantum computers, 2015 to 2019. And as you can see, these processors will work on subatomic level. They are based on some kind of very different kind of paradigm and different kinds of algorithm and almost different technology. So one day in your lifetime, obviously you would see this kind of quantum machines. So this, and you would be able to answer this fundamental question, which Alan Turing asked long ago: can machines think? So in the first lecture today, I wanted to give you an overall perspective of this computer technology, starting from very old, starting from the initial mechanical machine to the modern quantum computers and so on. And so later on, we'll gradually move on to, from the next class, we'll move on to, we're talking about this, how to design an overall computer system and so on. So any question at this moment? Okay. So if you are interested with the task of building a computer system, sometimes it appears as a mystery. So just like if you look into this cartoon, this is drawn by a famous cartoonist, Robinson. And it shows that how a railway engine is, locomotive engine can be built. So the basic question is, how to streamline a design process. I've taken this from, so there is a Bengali book by Satyajit Ray. So he used this cartoon too, and this is called Railgari Adiparbo. That means how the railway locomotives could be built, in previous times. So building a computer system is something like that. So the basic question is, where do I start? What are the design issues? Right? Okay. So before I finish today, I will just touch upon some basic concepts. One is called the system hierarchy. So at the core of everything, you have a basic machine, right? Which comprises some kind of electrical logic circuits. And the circuit comprises like adders, multipliers, shift registers, and so on. And so that we called bare machine. So you are looking inside the CPU. So inside the CPU, what do you have? So at the ground level, at the bottom level, you have only bare machine, right? You have already learned how to design combinational and sequential circuits, right? Combinational circuits, finite state machines, you have already learned that. Okay. So in the circuits, what do you have? Just focus on, logic circuits only. What are the components of a logic circuit?
Gates.
Gates, okay. So gates are combinational components, right? You
Latches.
have latches, okay, or flip-flops, right?
Yes, sir.
So latches can also be constructed by interconnecting gates. Agreed?
Yes, sir.
So you have combinational circuits. So you have basically a collection of circuits, right? Some are combinational in nature. That means whose output depends only on the present input. Some are sequential in nature, which emulates some kind of finite state machine. So that means the behavior of the machine not only depends on the present input, but also past inputs, right? Okay, so all logic circuits comprises combinational elements and sequential or the state elements, basically flip-flops, right? Or latches. Correct. So we are focusing only on logic circuits. Now, apart from logic circuit, in a machine there are other circuits which are called analog circuits. Say, for example, power supply of the machine, right? Which is not a digital, which may not be fully digital, because this is an analog circuit. Okay. So there are clock, or there may be clock generators. It may be there may be some kind of, say, in your mobile phone there are amplifiers, right? So that the signal is amplified and you can hear the voice. Okay, so those are analog circuits. So they perform continuously on various voltage and current levels. But logic circuits, they operate on zeros and one, right? Either 0 volt or some high volt, maybe 5 volt also. Okay. So let us focus on combination, just logic circuits alone. So we have a collection of gates or gates and flip-flops and so on. Those are called Baer machine. Okay. So we have several logic circuits, several finite state machine implemented, and so on. So consider this Baer machine as a black box. So it has certain logic inputs, certain logic outputs, and of course power supply and etc. they are. So when certain inputs arrive when certain logic values, that means certain strings of zeros and one appear at the input of the circuit generates certain logical values at the output. Agreed? In other words, this Baer machine, which is nothing but a collection of logic circuit, can interact with the external world using only strings of zeros and one. Okay. In other words, if I say that Baer machine or the Baer collection of Baer hardware can understand only strings of zeros and one, can understand only machine language. Is that correct? Okay. But you don't want to communicate with this machine using strings of zeros and one, but that would be too much complicated and cumbersome, right? So what do you need to do?
Translate.
One thing I can do that, suppose there is a string like zeros and one and etc., and this signifies some addition operation. So instead of writing a sequence of zeros and a string of zeros and one, I can compactly write add, okay, or shift, or move, something like that. And I maintain a table that if I say add, it means this string. If I say move, it means some kind of string like this. So collection of that is called assembly language, or this is called instruction set architecture. So by instruction set architecture, we mean the sequence of the set of strings, and each string has got some meaning, you know. Each string is intended to perform certain basic operation on the machine, you know. In other words, there is a virtual envelope on this bare machine, which is called the instruction set architecture, you know. Now, if we interact from this envelope, you know, so then you don't have to write in terms of zeros and one. You can write in terms of assembly language, like add, move, shift, and etc. So that your job has become, as a programmer, your job has become a little bit simplified, right? So this level, so when you observe the machine from this level, enveloped with the instruction set architecture, you know, so to you, this machine appears to you is capable of performing certain instructions like addition, subtraction, move, shift, etc. So that collection of instruction set, as what is visible to an assembly level language programmer, is called the computer architecture, you know. Okay. And when you look into the bare machine, where you have this, you know, these several components, several hardware components, how the components have been designed, how the internal components have been interconnected. So that is the domain of computer organization. Okay, so let us move ahead. So instruction set architecture is the envelope of this bare machine. And you don't want to, so how do I, and the machine does not understand the add or subtract those instructions. So you need some kind of software envelope around it, which is called the assembler. And using this assembler, at this level, you can use this kind of instructions. Say, for example, you can write add C, A, and B. That means, so there are registers A, B, and C. Maybe you add the content of register A to the content of register B and save the result of addition in C. And you write this instruction as add C, A, and B. So when you write this instruction, this assembler actually translates or transforms this assembly language into strings of zeros and one and fits to the bare machine. The bare machine can understand the strings of zeros and one, would execute those sequences one by one, generates those outputs, and those outputs again is reconverted into, you know, into readable form, and you observe the output in your terminal. Okay. So what does the compiler do? So you don't want to write languages like add C, A, and B. You want to write instructions in high-level language. For example, if X, then C equal to A plus B, else C equal to A minus B. Okay. So you have defined certain variables. You have some high-level language constructs like if then else. So that way you can write program in an easy way, right? But when you write this program and fit to this machine, the machine does not understand anything. So there is a layer of compiler. So what is the purpose of this compiler? Your compiler classes have started today, right?
Yes, sir.
Okay, so what does the compiler do? What is the input and output of the compiler?
Translates.
Right. So input is a high-level language like this, and output translates into machine language like this.
Binary.
Yes, optimizes, etc., and it produces a sequence of assembly languages. Okay. And that translation process is taken care of by this compiler. And this is a very involved processing. Okay. So once it is translated into machine language, the assembler translates into strings of zeros and one, and the bare machine, which is lying at the center here, then the bare machine would execute those machine language instructions. So this is the overall hierarchy. You know. So you have some understanding of, you know. So from the high level language, how it is being translated into a sequence of zeros and one, so that the bare machine can execute it. So this is a very involved process. It has to pass through the compiler, it has to pass through the assembler, and to reach the bare machine, it will be executed here, and finally it has to come back again to the outside world so that the result is readable to the outside world, right? So this is the overall system hierarchy. Okay, so in the next class onwards, you know, we'll talk more about it, and we'll gradually pass on to the details of computer organization and architecture. And so I hope that gives you an overall idea of the growth of computer technology and the overall computing system hierarchy. Okay. Any question here? Based on today's discussion? Please feel free to ask, you know. Okay. I'm going to stop today, and please let me know that if you have, wait a minute, sorry.